So in today's lesson, we're going to be extending our understanding of equilibrium law by performing some equilibrium calculations. So you will remember from yesterday that we can develop an equilibrium law by looking at the products and the reactants, and we know that our equilibrium constant is going to be equal to the concentration of our products raised to the exponent of their coefficients divided by that of the reactants raised to the exponent of their coefficients. And so if we know that, then we can employ some strategies to solve for equilibrium concentration. So you're going to see essentially two main types of calculations in this section. You're going to see either the case where you're calculating the equilibrium constant, that's KEQ, right? So really you're solving for KEQ, but you're given or have a way of finding equilibrium concentrations. The second type of question you might see is you're going to maybe asked to calculate one or more equilibrium concentrations using a known value for KEQ. So there are questions where they will give you that equilibrium constant at a given temperature, and you'll be able to utilize that and the equilibrium law to solve for some unknown concentrations. So let's take a look at a first example. In this example, I have the reaction of, and I see a little typo here, which I'm going to fix right away. I can see that it says N2O2, and that really ought to be N2O4. So let's just fix that right away. And so in this question, they're saying at equilibrium, the concentration of N2O4, let's fix this over here as well, N2O4, is 0.0292 moles per liter, and we also have the concentration of NO2 as well at 0.0116. So the question is saying find the equilibrium constant. So in this case, what they're asking me to find is the value of KEQ for this reaction. So a good place to start is to go ahead and write out that equilibrium law. So pause the video, take a minute, and go ahead and do that. Okay, so I know that my equilibrium constant for any reaction is going to be the concentration of my products raised to the coefficient of their raised to the exponent of their coefficient. So NO2 in this case squared, and divided by that of the reactant. So in this case I have N2O4. And so there's my equilibrium law. And so in this case, they're actually giving me my equilibrium concentrations. They're saying it's at equilibrium. And that is a really important point because you cannot substitute at just any concentration values into the equilibrium law to get the equilibrium constant. You must be these concentrations here must be equilibrium concentrations if you expect to obtain the equilibrium constant. So that's really important. And if you see that they're giving you equilibrium concentrations, this actually makes this a super simple problem because all you need to do at this point is to simply substitute the given values in. And I'm going to go ahead and do that. So 0.0116 moles per liter squared divided by 0.0292 moles per liter. And I'm going to suggest to you that you don't skip this step here of writing out the equilibrium law. I've seen many students make mistakes by simply going from their K equilibrium to substituting directly, and that's where you can make some mistakes. So I'm going to grab my trusty calculator at this point and sub that in, 0.0116 squared divided by 0.0292. And so analyzing this, I should have 3 significant digits in my response here, and so I am getting 4.61 times 10 to the negative 3. Okay, now unlike our rate law, we typically do not include units with an equilibrium constant, though we could. It's typically not something that is asked, so yay, we get to skip that part. So hopefully you found that question to be reasonable. It was sort of our entry-level question. I think we're ready to start a more complex example. So when I was changing the note to the next, the slide to the next question, I noticed that I did have this included in my note. Only equilibrium concentrations can be substituted in the equilibrium law if you expect to get a KEQ value at the end of that. All right, let me slide this up to the next question. Here we go. So there we go. So in this question, they're saying at a certain temperature, and you'll remember that, our KEQ value is only valid at a specific temperature. And then if we change the temperature, we alter the value of our equilibrium constant, so keep that in mind. So in this case, I have a mixture of hydrogen and iodine, and I've prepared that by adding a certain number of moles of each of those substances into a 1 liter flask. So it's important to remember that when we are analyzing equilibrium constants and laws, the values that are substituted into the equilibrium law have to be concentration in moles per liter. So the fact that we have a 1 liter fat flask tells us that we actually have 0.1 moles per liter of each of our reactants. So that's a little bit helpful. Okay, and so I have an equilibrium that's established. Here's the equation. The reversible equation. And so at equilibrium, they're telling me that I have a concentration of I2 that has dropped to 0.02 moles per liter, and I want to know my equilibrium constant for this reaction at this temperature. So a couple of days ago, we worked on constructing our ice boxes, and so I'm going to go ahead and construct an ice box for this situation. I'm going to encourage you to pause the video and set up an ice box for yourself. All right, so I'm going to try to get this into this little corner here. So I have H2 plus I2 going to make 2HI. And remember, I have my initial concentration, my change in concentration, and my equilibrium concentration. I'm going to make this a little bit bigger just to help me fit all of this in. There we go. And so the question is telling me the concentration of my reactants that I have initially, and they haven't told me anything about my product HI, so I'm going to assume that that is 0. And that's a pretty reasonable assumption to make. Unless they tell you any differently, it's reasonable to assume you have no products present when the reaction begins. Now I know that my products are going to both decrease and my reactants are going to decrease in concentration and my product's going to increase. The direction of the reaction is going to be, primarily forward, in the forward direction. That's simply because, again, I don't have any product at all at the beginning. So they're going to decrease according to their mole ratios. So I'm going to, my H2 is going to decrease by X amount, and so is my I2. But because of my my mole ratio here, I know the concentration of HI is going to increase by 2x. Now the question itself has told me that at equilibrium, my I2 had dropped to 0.02 moles per liter. So I'm going to go ahead and I'm going to substitute that in here. 0.020 moles per liter. And I can also develop expressions for other reactants and products. So my H2 concentration is going to be just 0.1 minus X. Because remember that my initial plus my change is going to equal my equilibrium concentration. So 0.100 minus X. Squeeze that in. 0 plus 2X over here on my product side is going to give me 2X. So the first thing I'm going to do is I'm going to recognize that I have all of the information to solve for X using the values given and the details given for I2. So I'm going to go ahead and do that. That's going to be my first step down here. Oops. So So 0.100 minus x is equal to 0.020. So x in this case is going to be 0.080 moles per liter. So now that I know that, I can develop equilibrium concentrations for both my H2 and my HI. But since I know the expression for I2 and H2 are exactly the same, I think it's fair to say that my concentration of H2 is also going to be 0.080 at equilibrium. Nope, that's not fair to say. Let me back up that truck. It's not fair to say that that's the concentration of it either. Simply X is equal to that. So let me keep going here. So 2. So let me back up. So I2, I know, has a concentration at equilibrium of 0.020 moles per liter. And it so happens that, again, because H2 and I2 have the same expressions, that I'm also going to say, well, that's my equilibrium concentration of H2. And I can get the equilibrium concentration of HI by substituting the known value for x, which is 0.080. So 2 times x is 2.080 moles per liter, which will give me 0.160 moles per liter. So now I haven't really answered the question because, of course, the question was, what is the KEQ value for this reaction? So my final step is going to be to just simply construct an equilibrium law, and then insert the equilibrium concentrations into that equilibrium law. So this I'm going to call step 3. So I know that KQ is going to be equal to the concentration of HI squared over the concentration of H2 times the concentration of I2. So HI, well, you'll remember it has a concentration of 0.160, and I'm going to square that value. This is a bracket. And then I've got 0.020 for both H2 and I2. So I'm simply going to square that. Okay, here's my answer down over here. Working that out. I'm getting 64. So the KEQ, the equilibrium constant for this particular reaction, given the concentration at equilibrium of I2, is 64. Hopefully you found that to be okay. I think we're ready to start a third calculation. So in this reaction here, I'm going to read through it, but I think it's one that you should be able to do yourselves. So I'm going to let you go ahead and give this a try, and then magically, when you resume the video after pausing, you will see my solution. So in this reaction, I have methane and water reacting to make carbon dioxide and hydrogen gas, and they are giving me the equilibrium constant at a specific temperature, but they're also giving me the equilibrium concentrations of 3 of my 4 species. And so the question is, what was the equilibrium concentration of H2O in this mixture? Okay, pause the video, give the question a try, and then come back when you're ready to see the solution. All right, so here is my solution to question number 3. So the first thing that I did was I went ahead and I created this equilibrium law given the chemical reaction equation. And I would encourage you again not to skip this step because people tend to forget to include those coefficients as exponents. And then I set up I substituted in all known values, so I know KQ, they give me that value in the question. And then I substituted in all concentrations as is because they told me that these concentrations existed at equilibrium. So it's safe to say that KEQ equals all of these concentrations because the concentrations are given at equilibrium. So then I only really had one unknown, and that was my concentration of H2O. So by rearranging my equation and solving for H2O, the concentration of H2O, I get 6.677 times 10 to the negative 2, and that's in units of moles per liter, of course, to 3 significant digits. And I analyze my result, and given all of the other concentrations, the value that I've obtained seems reasonable, and so I'm pretty comfortable with that. Hopefully you did okay with this question. Let's take a look at the next question. All right, so now we're raising the bar a little bit here. We're going to look at a question that is a little bit more involved, and it's going to ask you to employ some algebraic techniques that you would have learned in math class that we haven't really seen a whole lot of in chemistry yet. So prepare yourselves. So let's read through this question. So the reaction equation is given, and it's pretty much the reverse of one of the reactions that we just saw. And they're giving us a KEQ value in this question of 4.06. Now they're specifying the temperature here only because remember that the temperature is a factor that affects the value of KEQ. So this equilibrium constant is only valid at this temperature. And they're telling us that we have 0.100 moles of carbon monoxide and 0.100 moles of water, and we're placing them in a 1 liter vessel. So that actually makes things nice because then we have values of moles per liter, so concentration units. And the question is asking us, what are the concentrations of each of the reactants and products at equilibrium? All right. So I'm going to encourage us to first start by, take a guess, drawing or creating an ice box. So I'm going to do that right here. So initial concentration, change in concentration, and equilibrium concentration. I'm going to encourage you to pause the video now and try to construct an ice box, and then just ensure that you're on the right track with this. So I'm starting out with 0.100 moles of each of my reactants. So unless I'm told otherwise, I'm assuming that I have 0 concentration of products, which means that my reaction will be really strongly favoring the product side. It's going to be moving in the forward direction. So given this, my carbon monoxide is going to decrease by X, as is my water. The coefficients are all 1. It's all 1-to-1 ratios here, and so I'm just going to be increasing or decreasing by X. Here we go. So then that allows me to develop some, I don't know what any of the equilibrium concentrations are for any of these species, which is a little bit different than what we've seen. So the only thing I can do is write out some expressions. So I'm going to try to squeeze this in. So it's 1.00 minus X, 1.00 minus X, X, oops, and X. Remembering, of course, that initial plus change equals, I don't know what's going on here, equals, whoa, what is this business? I'm just going to get rid of that because I have no idea what it is or why that even happened. There we go. So there we have it. Now I'm ready to begin the step 2 of this, which is to create an equilibrium law. So I know my KEQ, pause the video now and establish an equilibrium law, and then come back when you have done that. So K equilibrium is equal to the concentration of my products, in this case CO2 and H2, raised to the coefficient, raised to the exponent of that is their coefficient. In this case it's a 1, so we're good. Divided by the same thing for my reactants. So CO times H2O. So there we go. I'm going to move this up just a smidge. I think I can do that. Oops, there we go. And the thing is now I actually have a KEQ value. It's 4.06. So I'm going to substitute that in. So 4.06. And I'm also going to substitute in all of the expressions that I have for products and reactants. So CO2 is X, so I have X times X divided by 0.100 minus X times 0.100 minus X. So there I go. I'm going to simplify this just a smidge. So 4.06 equals X squared over 0.100 minus X, all squared. And some of you may be frightened right now looking at this thinking that it's a quadratic expression, and that's, you know, it is. I've got some squareds here, going to have some other squareds here. But, you know, there may be questions where we may have to employ the quadratic formula in order to solve for our X value in order to then go ahead and go back and solve for equilibrium concentrations. I'm going to tell you that in this case I see something that makes life pretty easy, which is that I have a square in my numerator and a square in my denominator. So because both of these are squareds, I can go ahead and simply take the square root of top and bottom, and whatever I do to the left side or the right side I have to do to the left side as well. So now I know that I have, X over 0.100 minus X is equal to the square root of 4.06, which I can actually solve now if I want to. And that's 2.0149. I'm carrying a couple extra digits just because I just want to make sure that I don't round too early. Let me move. How much room do I have here? Oh, I've got a little bit more room. So this is now a linear equation that I can solve quite easily by simply bringing up my denominator up and then solving for X. So I'm going to just go ahead and quickly do that. Okay, remember, I'm just going to collect some like terms here. Negative 201x plus 1x is going to give me 301x. And then that leaves me with 0.201. So then I can get a value for x. And so my value that I'm getting for x is 0.6. Let me see how many sig figs. I need 3 sig figs, so 0.669 moles per liter. And so now I can go ahead and I can perform the final task. I'm going to call this step, where are we now? Is this step 3? Not sure. I can go ahead and utilize my value of x and these equilibrium expressions that I have right here to help me solve for the concentration of each species at equilibrium. So I'm going to go ahead and do that. So I'm going to do that in green. Concentration at equilibrium is CO2 is simply what the value of x is, which is 0.669 moles per liter, which is also the concentration of H2. Right? I know the concentration of CO is equal to the concentration of H2O at equilibrium, and that is equal to 0.100 minus x, which gives me 0.569 moles per liter. I just noticed a little typo over here, and I hope it doesn't affect everything, but I noticed this is 1.00. It really should be 0.100. I believe. Yes, it is. So even though I wrote it wrong, did the calculations as it was expected, and so we're good to go. All right, so hopefully that was okay, just a little bit more involved in terms of the algebraic solution, but hopefully manageable for you. This is the end of video number 1. I'm also going to be posting video number 2 to go through 2 final and more complex calculations, so super critical that you examine those and that you make sense of them, and then work through some practice problems that will be assigned to you.